Section 5.1 is referring to areas and distances, page 1. So in the previous section, which was 4.7, we learned how to use velocity to find the position, that was a really hard word to say, of a car based on when it applied the brakes. But we did this using the process of antiderivatives. This section, we're going to do the exact same thing, but we're going to actually do it visually or geometrically. So imagine that I'm given some sort of rate, and we know that a rate is a derivative. From there, we can find its original function, which is the distance or position function that it came from. So consider this first example over here that makes a little bit more sense. Imagine I have some constant rate. So as time moves on, the rate in this particular problem is staying constant. Well, since rate is the distance that we have traveled over time, then we have gone to t to the right. I don't know how to word that, but it creates this space under the rate constant function. And we know how to find the area of a rectangle. So we can use that if we take how long we've been traveling times the rate that we were going, those multiply together to give us the area of the rectangle, which is the total distance that we've traveled. Well, the same thing is going to happen in this picture on the right, except for rate doesn't tend to be constant. Usually it varies, and we see all sorts of increases and decreases, speeding up and slowing down, even if we're not in traffic. But it turns out the amount of distance we've traveled is still that shaded region. So the fact that the rate is changing doesn't change the concept. So imagine in example 1, I'm given this graph, and they're the identical same graph on both sides, f of x. And I'm asked to write some sort of expression to approximate r, where, as you can see, r is the distance or the area under the curve between points A and B. Well, what happens here is I know how to find the area of a rectangle, but I don't have a shape like this. It's not even a basic trapezoid shape. So instead of using the shape on the left, we're going to take that exact same shape and we're going to chunk it into a bunch of rectangles, some finite or set amount of rectangles, and we can find the area for each of these rectangles and then add all of these areas together. So when we're approximating the area under the curve and we're using that finite or set number of n rectangles, we need to specify what point we're using for the heights of the rectangles. We'll go back and look at that in a minute. But notice when it comes to the width, we're using the exact same width, delta x. Notice this first rectangle, we didn't use the left endpoint of x1, 0. We did not use the right endpoint of x1. We didn't even use the midpoint. We used where it kind of is hitting the graph. So we need to be able to discuss that as a concept, and that's what we'll see in the next pages.